I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we will discuss the topic unit saturation, that is vanishing gradient problems. First introduction. What is saturation? Unit saturation is also called the vanishing gradient problem. That means unit saturation refers to the condition where certain neurons in the neural network become saturated due to the use of specific activation functions like sigmoid or tan H. This condition results in the derivatives of the activation functions becoming extremely small, which causes the gradients used in learning to vanish during backpropagation. This is why the phenomenon is more commonly referred to as the vanishing gradient problem. It occurs during backpropagation in deep learning, deep neural networks. Backpropagation is the algorithm used to compute gradients in the neural networks, and it works by applying the chain rule through each layer. In deep neural networks with many layers, the gradients calculated during backpropagation can become extremely small as they move backward through the network, particularly when activation functions that squares input to narrow output ranges are used. Next, the activation like sigmoid or tan H causes the gradient shrink. In the sense, the sigmoid and tan H activation functions have the derivatives that are significantly less than 1 in most input ranges. When these small derivatives are multiplied across many layers during propagation, they can cause the overall gradient to shrink exponentially, which prevents effective weight updates. Next, gradient become too small to effectively train each layers. Since gradients are the signals used to update weights and biases during training, small gradients mean minimal updates. This particularly impacts the early layers of the network, as the gradient values diminish by the time they reach these layers. As a result, these layers may not learn meaningful patterns from the data. And finally, it hinders learning, especially in deep or recurrent net. In deep and recurrent neural networks, unit saturation is more pronounced due to the number of sequential operations. The vanishing gradient problem severely limits the network's ability to learn long-term dependencies or abstract patterns, making training unstable or ineffective in these architectures. Why does it happen? The vanishing gradient problems become significant in neural networks with many hidden layers because the depth increases the number of multiplications of small derivative values during backpropagation, and this leads to an exponential decay in gradient magnitude. Common in recurrent neural networks, that is RNNN, and deep feed-forward networks are particularly vulnerable to this problem. RNN deals with the sequence and depend on retaining memory through repeated applications of weights over time steps. An operation similar to deep, that is unrolling, making them especially sensitive to vanishing gradients. More severe when using the sigmoid or tan H. Sigmoid and tan H are traditional activation functions that compress a wide range of inputs into small range. The derivative values approach zero for large positive or negative inputs, making them a key cause of gradient vanishing in deep networks. Next, the deeper the network, the worse the problem becomes. Each layer in a network contributes a factor to the chain of derivatives used in backpropagation. In deep networks, this accumulation of small values leads to gradients that are essentially zero by time they reach initial layers. Finally, the gradient-based methods like SGD, stochastic gradient descent, are especially affected how means gradient-based optimization algorithms such as stochastic gradient descent rely directly on gradient values to update weights. When gradient vanish, these methods cannot effectively adjust weights, slowing or halting learning together. The backpropagation process, first point, backpropagation uses the chain rule to compute gradient layers by layer. Each layer's gradient depends on the gradient of the subsequent layer, meaning error propagates backward through the entire network. Next, In the chain rule, the gradients from all layers are multiplied together. If any one of the layer has a derivative less than 1, which is common with the sigmoid or tan, the final product of these derivatives can become very small. If each derivative is less than 1, the product becomes very small. Even if the derivative is moderately small, the repeated multiplication results in an exponentially decreasing gradient. This makes it linearly impossible for earlier layers in the network to receive a meaningful error signal for learning. Early layers receive non-zero gradients. Due to the compounding effect of small gradient, the layer closer to the input receive extremely small values during weight updates. This means they do not learn useful representation and their parameters remain nearly static. As a result, their weights and biases hardly get updated. How means because early layers fail to receive adequate gradient, the optimization algorithm does not make significant updates to their weights and biases. This lack of adaptation limits the ability of the network to recognize basic data patterns or extract meaningful features. Next, the role of activation function. The first one is the sigmoid and tan h. How it is? Sigmoid maps any real valued number into range 0, 1, and the tan h maps minus 1, 1. This compression, while useful for contributing output, also causes the function to become nearly flat outside a small range input, which limits gradient flow. The derivative are small when input is large or small. The derivative of sigmoid or tan h are close to 0 when the absolute value of input is large. This is because the function output saturates in these regions, and a flat slope means no significant change in the output relative to input. Example, if a sigmoid derivative approaches 0 when x is large, modulus of x is large. For values of modulus of x is greater than 3, the sigmoidal function produces the output extremely close to 0 or 1, and its derivative is almost 0. This low sensitivity to input changes effectively kills the gradient at that point. This saturation flattens the output, killing gradients. In the saturated region, if the of the sigmoid or tan h function, the near zero slope leads to derivative that cannot pass useful information backward through the network. This make it impossible for the model to learn from such activations. Activation squares the signal, making learning effective because of the squashing effect, the signals, that is gradient, passed backward or weakened to the output point of the being effective. This hinders training and makes it especially difficult for deeper layer to correct errors. Why it's a problem? That is, in deep learning, early layers are responsible for capturing basic patterns like edges or textures in images. If these layers are not trained properly, the higher level understanding built on top of them will also be flawed. If these layers does not learn, the network can't learn complex features. Means when early layers fail to learn due to vanishing gradients, the network misses the foundational understanding of the input. As a result, deeper layers have poor input to work with the struggle to learn complex abstractions or patterns, and leads to slow convergence and low accuracy. Because the gradients are too small for effective weight updates, training progresses slowly. Even with many epochs, the neural networks may not converge to a good solution, leading to proper accuracy on both training and testing data. And the training becomes inefficient or completely fails. In the sense, in several cases, the training process may stall entirely. This means that the loss does not decreases. The performance metrics do not improve regardless of the number of training iterations. Network appears to be learning, and but output remains poor. A deceptive aspect of this issue is that the loss may decrease slightly, creating the illusion that learning is happening. However, due to inactive early layers, the overall output remains suboptimal and the model performs poorly in practice. Next, visualization of the problem. Sigmoidal output ranges from 0 to 1. The sigmoid activation function compresses any real input into fixed range between 0 and 1. While this helps prevent extreme outputs, it also limits the effective range in which learning can occur. Next, the derivative of the sigmoid is largest when the input closes to 0, but it quickly drops the near 0 value when the input moves away from this region. This sharp fall off causes gradient to vanish outside a narrow input band. For example, if modulus of x is greater than 3, the sigma derivative is closer to 0. In practical term, any input larger than 3 or smaller than 3 result in nearby flat sigmoid where the derivative is close to 0. This creates dead zones in the activation landscape where no learning takes place. When chained or over many layers, gradient vanish complete. At these near zero derivatives are multiplied over many layers during propagation, the resulting gradient becomes insignificantly small. This cumulative effect and renders deep networks incapable of effective learning. And what is the result about this? The dead neurons that don't update during training. These dead neurons refer to the network unit that output constant values and receives no updates during training because their gradients are too small. Once they stop changing, they stop contributing to learning together. And the solution one for this problem is the ReLU function. We have to use it. This is very simple and effective. And the derivative of the ReLU function is 1 for x is greater than 0, otherwise 0. And it avoids small gradients for positive inputs. And it helps preserve gradients in the deep layers. This ReLU function, derivative of the ReLU function, it is widely in the CNN and the deep learning architectures. You know what do you mean by convolution neural networks and made deep learning application due to its effectiveness and simplicity. And the solution to residual connections. Residual connections were introduced in ResNet architecture to allow the training of very deep network by directly addressing the vanishing gradient problem. And we add the identity shortcut f of x plus x and gradient bypass for the nonlinear system. It keeps gradient flowing even though deep blocks, and it greatly improves training in very deep learning networks. That means residual connections have revolutionized deep learning by enabling them training of networks with hundreds or even thousands of layers, something previously impractical due to vanishing gradients. And the solution 3 is the batch normalization that we are going to discuss in detail in the next lecture. Normalize the input to each layer. Batch normalization, that is BN, standardizes the input to each layer by adjusting it to have zero mean and unit variance across each mini batch, improving training. Next, by keeping inputs within our optimal ranges, BN ensures that activation functions like sigmoid or tanh do not enter saturation and zones, thereby maintaining useful gradients. Next, reduce internal covariate. BN minimizes internal covariate shift, the change in the activation distribution caused by parameter update, thus helping each layer receive stable input throughout training. This stability in input value helps prevent the gradient during backpropagation, allowing consistent and efficient learning across all layers. Often improves both speed and accuracy of training by enabling higher learning rates and reducing sensitivity to initialization. Batch normalization not only speeds up convergence but also often leads to better overall model performances. And coming into the summary, vanishing gradient is a core problem in training deep network. That means the vanishing gradient problem possesses fundamental challenge in deep learning, making it difficult to train very deep networks effectively without special techniques. And the second one is the root causes lies in activation function like sigmoid and tanh, which compress inputs and yield small derivatives, especially for large input magnitudes, lead to ineffective learning in easy layer. And third one is as gradient vanish, the early layers receive the little to no update, preventing the network from learning basic pattern and causing poor performance. And what is the solution for this is use ReLU residual connection and bottom batch norm. Modern deep learning frameworks solve this by using ReLU to avoid small gradient residual connections to allow gradient flow and batch normalization to stabilize activations. Understanding and mitigating it is crucial for deep learning success. How successfully training deep networks depends on understanding these gradient related issues and using the right strategies to overcome them, enabling the full power of deep learning models. Hope everyone understood about this topic. The remaining things we'll discuss in the next lecture. Thank you.